by chance? And so out of chapter 9.
11C.
On the first one,
Yeah.
first assignment, problem 11. All right. So this was estimating a proportion of adults who have high-speed internet access. What size should be sampled if they want to? Wait, did you say part C?
Or part B.
Okay, I was like, this definitely doesn't have a part C. They want to get it within 0.04 with 95% confidence. If you use a previous estimate, or if you use no estimate. So this is what I was. So yesterday when I was mentioning, or when we first started talking about this. Blah, 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 blah. Where'd it go? Here it is. So you can do this is the conservative estimate if you have no assumption about what the true proportion is. But if you do have an idea of what the proportion is, you can use the actual like margin of error formula. So this is saying do it both ways. So the first part of this problem is saying, let's say you use a previous estimate. Then if you're using a previous estimate, like a previous p hat, then we can just use the general margin of error formula to solve for n. So let me bring up a new blank presentation here and go here. So the idea here would be that, the margin of error formula says, it's z alpha over 2. This is the margin of error for that particular, circumstance. But so this is if you know previously some p hat. Now the thing is that's not super reasonable necessarily, just because, that's the whole point of taking a sample, is you're trying to estimate the proportion. So if you had a pretty good estimate in the past, you might question why you're taking another sample. But if you think it hasn't changed that much, it might make sense to use. So in this case, for the first part, we're just going to use this formula. So you can solve this, but I usually just plug it in. So in this case, we wanted a margin of error of 0.04. I can't remember what the confidence level was. 95? Yeah, so in that case, you would go, the z would be 1.96, and 0.46 times 1 minus, that's going to be 0.54 all over n. And we're going to solve for n. That's how you're going to do this. So, you would divide this side by 1.96, and that would leave you the square root, so you probably square both sides. So that would leave you with 0.46 times 0.54 over n on the right-hand side. And then you would swap out. So it would end up being, I think what you'll end up with is 0.46 times 0.54 times, this will come over as the reciprocal, like that. So whatever that comes out to be is how you would solve it. But you're basically solving this equation. Yeah. And, but in the second part, we'll just do it real quick because we're already here. So what does that come out to be? Anybody got one? I get about 596.4. Anybody else get that? Yes? No? Maybe so?
Yeah.
So I got 596.4, which we should probably round up to 597. All right. Let's see if it likes that. I think it wants us to round up. I always round up. Cool. Now it's saying, but what if you don't want to use any prior estimates? That's when we need to use this conservative kind of guess. So this one right here. So we're just going to use n's going to we're going to do that 0.25 times z alpha over 2 over your error squared. This is going to end up probably giving us a slightly bigger sample size, but so it's going to just be 0.25. Our z alpha is still 1.96, and the error we want is still 4. So I think, where'd my thing go? Let's see what that comes out to be. So I get 600.25. Anybody else get that? 600.25? Yeah? No?
I got the same thing.
Okay. 600.25, which I would probably round up to 601. Is that more than the other one? Yeah. So that's what I would think they're looking for. So let's see if it likes it. Yeah. Okay. Yeah. Does that help? Yeah. So it just depends on which one you're looking for. You know, actually, I solved from the actual error formula. So this is it's pretty, right? This is a conservative estimate, this formula. But if you actually had that, it would just be p hat times 1 minus p hat for part. You'll notice that's actually what we ended up doing. It was p hat times 1 minus p hat times z over e squared. So you could also just shortcut if you like formulas and shortcuts. I have a hard time remembering all the formulas sometimes. Then you could that's technically the estimate if you knew p hat, but because we usually don't, we just use a conservative estimate where we say, well, the most this could possibly be is a 50-50 split. So 50% times 50% is 25%. So that's our conservative estimate. Yeah? Yeah. Good question. All right. What else? Any other questions from the homework? No other questions? Perfect. All right. So let's go back to where we were yesterday. Yesterday we were talking about what? Where did we get to? Ah, yes. Yes. We were having problems because now we were saying, okay, so suppose we're not interested in the proportion. We're interested in the sample mean, which is really cool because the central limit theorem applies to the sample mean, and you know, with the central limit theorem, that's how we actually derive that confidence interval for the proportion. So that was cool. So we could just use the same strategy here and make this this nice interval another z interval. Problem is that it relies on the population standard deviation, which realistically we probably don't know, right? So then we said, okay, well, what if we just estimate the population standard deviation? We can do that because we have a sample. So you estimate it. It's a pretty good guess. You plug it into the formula. The problem is that also doesn't work because what we know from past research is that if you just plug in that sample standard deviation, the central limit theorem doesn't really apply in the sense that it doesn't converge to like a z distribution, but it does converge to another distribution, which we have we call the t distribution. All right. And so what we're going to do is rather than form a z interval like before, we're going to estimate the standard deviation, and we're going to actually make a t interval, and that t value is going to come from what's known as the t table. So I'm going to give you some t tables. They look a little bit like z tables. So you will pass it around. Pass it around. Just something
What
like
is
that.
this formula called?
This is the confidence interval formula for a sample for a mean. There's probably some left over.
No, that's not a C. It's a T.
We pass it out.
Going back.
Everybody going? All right. So now that everybody has a tea table, I have one on my computer too. So here's some things about the tea distribution. Okay. So and this is actually really cool. It helps us out a lot. So the tea distribution, a few things about it. So first off, it's sort of like a heavy-tailed Z distribution. Right? I showed you that picture yesterday. This one. So whereas the Z distribution has that nice bell shape, the T distribution, it looks sort of like a bell shape, but it's like a bell shape with a narrower center and longer, wider tails. These heavier tails. Okay? Now the nice thing about the T distribution though is that it changes based on the sample size. Okay? So and it turns out, right, so as N gets big, right, then the T distribution actually starts to look like the Z distribution. Okay. So as you take more and more samples, those tails start to get less and less heavy, and it starts to look pretty much exactly like a normal curve. And that's actually really nice and ideal because you can imagine, right, as you take more and more samples, what do you think is going to happen to your estimates? Like sample mean and sample standard deviation. The more samples you take, what's going to happen to those estimates? Are they going to be better or worse? They're going to be better, right? And so the more samples you take, the closer that sample standard deviation will be to the true standard deviation, and the mean will be the true mean. And so your estimates are getting really good. So you would expect that your confidence interval should look more like the Z distribution. Now, the nice thing about this, though, these two things, is that with a T distribution, small samples are okay. That's the nice thing about it. We don't okay. Small samples are actually okay. We don't have to worry about the size of our sample because the T distribution for small samples is going to have really heavy tails, and it's going to take into account those small sample sizes, so it's going to widen that interval for you. So you can actually take smaller samples. Now, granted, if you take really small samples, you might end up with a super wide interval, which might not be useful, but at least it's possible. So before, we were talking about you need to take 30 or 100 or whatever samples. With T intervals, we don't need to do that. We could take 15, 20 samples. The values, there's something we call the degrees of freedom. You might just see that as like DF. And the degrees of freedom are n-1. It's like the sample size -1. So your T values are going to be based on your degrees of freedom. All right. So here's how you actually use a T table. So let's say that you went out. Let's say that you go out and you sample, let's say you did a small sample size. Maybe you only sample 21 people. And then you calculate, say, their sample mean, I don't know, doesn't really matter, let's say salary. And what you want to do is your goal is to construct a 95% confidence interval. All right. So I know that the confidence interval formula looks like this. Right, that's the formula I gave you yesterday. what we need to do is we need to figure out what is this t value going to be. Okay. So the first thing we need to do is we need to establish our degrees of freedom, our alpha level. Okay, so the degrees of freedom is always n minus 1. And so what would be the degrees of freedom on this particular sample? Yeah, we'd say there's 20 degrees of freedom. And what's our alpha level here? If we're having 95% confidence, what's our alpha level? 0.05. Okay. So if that's the case, what is alpha over 2? So 5% divided in half. 0.025. Okay. So what we're looking for is we need t sub 0.025 with 20 degrees of freedom. So now we're going to go to our t table. All right, so I'm going to pull that up. I have it here. It's just beyond, in the book it's just beyond the z table, but somewhere back here. I think it's right around here. There we go. So t sub 0.025, right? Remember the way we're looking for, that's the place where it's like what we're looking for on the t table. Just like with the z table, we're looking for the place where 0.025 is above, right? And so we go to our t table here. So we're going to be on this column, right? Because we're looking for t sub 0.025. So I know my t's value is going to come out of this interval, or out of this column. And then I scroll down to the intersection of the alpha over 2 and the degrees of freedom. So what's going to be our t value? It's right here. So it's going to be 2.086. You guys see that on your table?
No.
So on the t distribution, we're looking for t sub 0.025 because our alpha level is 5%. So go to the column that up there where it says 0.025. Now scroll down. Now notice on the column over here you're tracking your degrees of freedom. So scroll down to 20 degrees of freedom and over to 0.025. And that's where you see 2.086. Okay, you guys all see that? Okay, so that's going to be our t value here. Whoa, where am I going at? 2.086. So for our particular example, we're going to use a multiplier of 2.086 rather than what would we have used for 95% confidence previously? We would have always just used 1.96. And now notice our multiplier is a little bit what? Bigger or smaller? And what's that going to do to our interval? We used to be multiplying by 1.96. Now, because we're using a t interval, it's 2.086. How's that going to affect our interval? It's going to make it wider. And what we're doing basically is we're pushing that interval out a little wider because we need to go a little wider because of the uncertainty we have in the estimation of our standard deviation. Right? So we got to push that out a little bit. All right. So, and if you notice, down at the bottom of your t table, scroll down to the bottom, right, all the way down. What happens as you take more and more samples? That t value is approaching what? All the way down to, so scroll down that column, right? 0.025, that center column. If you scroll down to the bottom, at the very bottom, what is it approaching? 1.96, which is the z value. Yeah. And just like you can scroll over right next to it, 1.645 for 90% confidence intervals, 2.576. That's about what we were using for our 99% confidence. Okay. So, anyways, you can see it's approaching this value, right? You know what I mean? So the more samples you take, the t intervals actually turn into z intervals as you take more and more samples. All right? Cool. All right, so far so good? So it's pretty much the same process. We just have that extra step. Now we got to go get our t-value first. All right, so let's say we look at an example here. I need some blank slides apparently. I'm running out of stuff here. All right. So let's say that you go out and what you want to look at is CBC students and from those 130 CBC, actually no, let's just do we have our own class here, so we can just do our own sample. How many people we got in here today? How many people we got? 1, 2, 3, 4, 5, 6, 7. 25. About 25? I got 25. So let's say you sample 25 CBC students, and now are you guys actually a random sample of CBC students? No, you're not, but that's okay. And I'm interested in calculating is I want to know about the number of hours per week you work. Okay, so that's what I want to see. Maybe I treat you guys like 25 randomly selected CBC students, which you're not, but let's say you are. Okay, let's say somehow I picked you randomly, and I want to observe how many hours per week people work. Okay, so let's say you don't have to know exactly, obviously, but let's see what. Let me bring up Statcrunch, and we'll just put the data directly in. Maybe. All right, so let's say, let's just go around, and as we go around, just tell me, just about, on average, about how many hours per week do you work. So some of us will work 40, some of us will work none, or whatever, but let's just go around. So let's start up here, and let's just go through. About how many hours? How many?
20.
About 20, okay. 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 All right.
10.
All right.
35.
All right.
36.
All right.
35.
35.
0.
Okay.
0.
All right.
90.
Right.
0.
Yeah.
35.
35. So let's go back to the back row. So let's start with 5. Okay.
20.
20.
35.
16.
0. 0.
43.
Okay.
25.
Uh-huh.
42.
How many?
42.
42. Okay.
25.
25.
25.
25.
41.
41. Shoot, some of you guys work more than me. All right. Good on you. All right, so let's see. So we got the sample, right? So from our particular sample, let's say you guys are 25 randomly selected. I'm going to go ahead and get our sample mean and standard deviation. Right? So in our class, you guys work an average of 20.64 hours and with a standard deviation of 15.17, let's say. All right, so remember those, 20.64, we'll say 15.17. And let's pull it over there. So from there, from our sample, it was, so our X bar was it 20.64? And our standard deviation was 15.17. So we're averaging a little over 20 hours, but that's pretty variable, actually. That's pretty high variability, which kind of makes sense because we have anywhere from like 0 to 42 hours. It's a pretty small sample, so there's a lot of variability in there. All right? So what I'd like to do now is, let's say with this, let's take that information, and let's say if you guys are a random sample, let's calculate a, I don't know, let's do a 90% confidence interval. For the true mean number of hours worked per week of CBC students. Okay. Because you guys are only a portion. So there's a good chance the truth of the population overall is maybe a little higher or a little lower, right? So let's do it. Now the first thing we need to do though is we need to go get that t-value. So given the confidence level I picked, what's our alpha level? 10%, yeah. So with 90% confidence, our alpha level is 10%. So what would alpha over 2 be? 5%. What's our degrees of freedom here? So there's 25 of you, so what's our degrees of freedom? Yeah, 1 less is 24. So we need to go find t sub 0.05 with 24 degrees of freedom. T sub 0.05 with 24 degrees of freedom. So you go to your table, go to your t table. Where's my t table? Here it is. So t sub 0.05, that's the what, 1, 2, 3, 4, fifth column. T sub 0.05. Scroll down to 24 degrees of freedom, and it's right here. What do you get? 1.711. 1.711. Everybody able to find that? Okay, so 0.05 is our alpha over 2. 24 degrees of freedom, 1.711. Perfect. So that's going to be our multiplier, 1.711. And now we're good to go. We got everything we need. Our formula says take x bar plus or minus t alpha over 2 s over root n. Yeah. And then, so that's going to be, our sample mean was 20.64 plus or minus, our multiplier is 1.711. Our sample standard deviation was 15.17, and our sample size was 25. So, what do you get for that margin of error? Let's do 1.711 times 15.17 divided by root 25. And give me just the margin of error first.
I got 2.98.
2.98. Anybody else get 2.98 for the margin of error? Seems like it should be a little bigger than that to me. Seems like it should be closer to maybe 5 or 6. But I could be wrong.
Because you just do the 1.711 times the 15.
0.17? Yeah, and then divide by root 25.
I got 5.19.
5.19? 5.19, yeah. So 5.19. So basically it's like our best guess is 20.64, but our margin of error is like 5 hours. And that's because it's a function because we took a small-ish sample and it was pretty highly variable. So then our actual interval would be what? So 20.64 minus 5.19, that would take you down to what? 15.45? Is that right? Somebody confirm that. I don't. Okay, cool. And then it would take you up to 25.73. 83? 8.3? Yeah. 8.3. Good catch. All right. All right. So then the interpretation of this would be what? We are how confident? So we say something like we're 90% confident the true average number of hours worked per week by CBC students is somewhere between 15.45 and 25.83 hours. So we think the true mean is probably somewhere between 15.5 to 25.8, 26 hours. Seem reasonable? Does that seem like probably a pretty reasonable range if you're talking about the average of the whole college? Yeah, probably. Yeah. All right. What questions do you have on that one? Any questions on that one? No questions on that one? Okay. So now one thing you can use Statcrunch does all this for us actually. So notice so there are going to be some examples in your homework where they actually give you raw data like we just collected. So you can use Statcrunch to calculate the mean and standard deviation just like we did there. like we were doing back in chapter or something, 3, 4-ish. That was under summary stats. But Statcrunch can actually also do the intervals as well. So you'll notice one of the options here says T-stats. Yeah. And so if you go into one sample T-stats, so like here, since we actually had the data, like the raw numbers, you can actually just select that, and you can choose to do a confidence interval, and you get to pick your confidence level. So like say we did a 90% confidence interval, and if we compute that, do they get the same numbers as we got? Yeah, see they give you the lower limit, 15.45, upper limit, 25.83. Is that what we got? Nice. Hey, we did a good job. We did a good job. Yeah. So again, that's, yeah, I'll show you again. So that's in stat, T-stats, one sample. Now it kind of depends if you have the data. Like, so in this case, we had the raw data, right? If you didn't have the raw data, that's actually okay. You can do it with summaries. So like say that you don't have the actual numbers, but you know the mean, standard deviation, and sample size. So if I picked a summary here, what was our sample mean? 20 point what? 20.64. So you can plug in the mean, 20.64. You can plug in the standard deviation, that was 15.17, correct? And you can say how many people you sampled, 25. And tell them that you want to do a confidence interval, 90%. So same thing. So now instead of like reading the raw, all that Statcrunch is going to do is if you tell it with data, it's just going to compute the mean and standard deviation itself and then do the interval. But if you don't have the raw data, you can just give it the mean and standard deviation and compute it, and then it's also going to give you, right, the same results. So 15.45 up to 25.83. So you can do it both ways. So you just have to choose in T-stats one sample. Do you have the raw numbers? Like, if you're in a homework assignment and you open the table in Statcrunch and you have the raw data, like the actual numbers, then you would say with data. If Statcrunch doesn't give you the raw data, it just gives you the summary statistics like mean and standard deviation, then you can just pick with summary. Yeah. You can actually do this as well for the proportion confidence intervals. I forgot to show you this, but I'll show it to you now, and it could help you on your homework. It at least helps you to check to see if you get the right answer. Because notice, what's the thing right under T-stats? Proportion stats. Yeah. So we have one sample. So again, if you had like actual counts, you know, like the actual data, you do with data, but you could also do it with summary. So let's go back. We can scroll back to one of those examples we did a while ago with proportions. Let's say, what was it, like back here, right? So 1,000 Americans, 180 don't like Valentine's Day, and we wanted a 95% confidence interval. So if we go back to our calculator here, we saw 180 people out of 1,000 that didn't like Valentine's Day, and we want to do a 95% confidence interval, and we compute that. It'll actually, there you go, what, 0.156 up to 0.204, and let's see if that matched our results. Oh shoot. Yeah, right. 0.156 up to 0.204. So it actually, I don't know why I opened that, but yeah, same exact results. So you can also get it that way. So for means, you're in T-stats because that's a T interval. Just for proportions, just pick proportion stats, and it'll let you do the. Yeah, pretty cool. Yeah. Yeah, I don't know. I think it's pretty cool. All right. Any questions about the actual calculating the T interval, though? The one we just did? You guys have questions about that? Or you feel okay about it? Okay, so you know your sample size gives you degrees of freedom. With your alpha level, that gets you your T value, and then it's just plug and chug. Right? Okay. Now, of course, let's see. So the question that we had with the question that we had earlier was, well, what if we want to control our margin of error? Right? What if we want to control our margin of error to like a certain point, and we want to get it down to a certain value? Then we might want to try, how big of a sample. We might want to also answer the question, how big of a sample? Okay. Roughly. So what we do is, you think about back to this formula, right? This portion right here, this is our margin of error, right? So our error is T alpha over 2 S over root N. But there's some sort of practical problems here to somehow solving for N in this case. And what are some of the practical problems here that are going to give us trouble if we're trying to solve for N in this formula? What are some practical problems? Because there's at least two. There's at least two problems here. What's at least one of them? So remember, this is before you take a sample or something. You're trying to figure out how many samples to take. Right? So I'm saying, I'm saying, okay, I want my margin of error to be. So let's say you're taking the CVC students and you're trying to estimate their hours per work. Maybe I want my margin of error to be within 2 hours with 95% confidence. Right? So I want my margin of error to be 2 hours or less. So I know the error I want. I don't know the sample size, but what's the issue here? And I'm trying to predict N. Like, what N should I use? So there's one problem. One problem is that S comes from the sample we haven't taken. That's one problem. So that's kind of a big issue, right? It relies on a standard deviation which comes from the sample, but you haven't actually taken the sample yet. You're trying to figure out how many people to sample. So that's a problem. There's a problem with this too. What's the problem with the t-value? And it has to do with this table right here and the sample size. So the degree, as your sample size changes, your degrees of freedom change, so what happened to the t-value? The t-value changes as your sample size changes. So this is a problem, right? Not only are you trying to use a number that you don't know, but then you're turning around and saying that, that t-value is totally different as well. So you got a lot of problems here. Now, what do we know about the t-value, though, as the sample size gets big? It gets close to the z-value. So our workaround here, and it's not perfect, our workaround here is to say, okay, here's how we'll do it. I know that the z-value is at least pretty close to the t-value. So the way we work around this is we say, okay, let's use the z-value because it's fixed. And then what we'll do is you take sort of a preliminary small sample to estimate that S. That's the way we typically do it. So, or you use prior information, or you take a really small sample up front, and you calculate the sample standard deviation of that, and you say, okay, I think this truth is probably something close to this. So you use that preliminary standard deviation in the z-value, and that's how you kind of get. That's how you ultimately make that guess. It's not going to be perfect, but it's at least going to give you a starting point. All right? So this is the way we tackle that. I mean, the t-value is just a non-starter. We can't do that because it just changes as your sample size changes. So the best we can do is z. All right. So let's go with let's look at the example with the working hours that we just did, right? So in our example, let's treat us like a preliminary sample, right? So our preliminary sample showed that the standard deviation of hours worked per week of CBC students is 15.17 hours, right? And our margin of error was pretty big, right? It was like 5 hours. So my question would be, let's say, how many samples would be necessary to reduce our margin of error to, how low would you want to get it? Hour, 2 hours? What do you think? What do you want? I don't really care. You choose. You want to get your error down to 3 hours, 2 hours, 1 hour? 2 hours, okay? To 2 hours or less. And what confidence do you want to have? You choose.
90.
Okay, so we'll just stick with 90% confidence. All right. So all we'll do here then is we'll say, okay, so then we have this formula for error, right? So I got this backwards. I know my error, I know the margin of error that we're going to go with is approximately going to be about z alpha over 2 s over root n. Okay. I know I want my margin of error down to 2 hours. If I'm doing 90% confidence, what's the z multiplier for 90% confidence? Isn't it 1.645? Right, for 90%? Look on your table. I think it's 1.645. Yeah. Our sample standard deviation was 15.17. And we're trying to figure out the sample size. Can we solve for n here? Can we solve for root n here? Or n by itself? Yeah, we could you could cross multiply. So the root n would come over here. And the 2 would go downstairs over there. And then to solve for n, what would you do? You would square both sides to get rid of that root. So our sample size is going to be whatever 1.645, not 1.65, 1.645 times 15.17 divided by 2 squared is. So what does that come out to be? Takers on that? So 1.645, 15.7 divided by 2 and square it. What do you get? I'm guessing maybe 140 to 160, somewhere in that range. I'm guessing. I have no idea.
156.63.
156.63. So anybody else get that? 156.63. Any other takers for that? Yes? No? Going once? Anybody get something different? Nobody got anything? I feel like I see a lot of people using calculators and nobody is volunteering any numbers. He said 156.63.
Mine's going to be wrong. It's
Okay.
Not, we put a 4 or 5.
Okay. Okay. 155.68. So 155.68, which we would probably round to what? 156? 156. Always round up. I mean, this one would have rounded up anyways, but we always round up regardless for sample size. So you'd say, okay, if you're going to try to get it down to that level, you got 25 samples. You really need 156 if you want to get it down to that kind of margin of error. All right. Now again, you'll notice that all we did was like solve algebraically for n. So we could have done that up front at this point. So when we were like e equals z alpha over 2 s over root n, you could do the same exact steps and then square both sides. And so you can get a general formula here. The sample size is going to be z alpha over 2 times s over e squared. Right? Okay. So you can use that if it asks for a sample size. All right. So, kind of like in probability. Well, I don't know. I think it's a little easier than probability in a sense, but the biggest confusion I get from a lot of people is when to use which circumstance. So basically, at this point, we've covered two things, right? What have we covered? Two statistics. Why do I keep going? So we've been looking at two things. We're either going to be interested in estimating a what or a what? A proportion, right? Right, so that's going to be P. Or we're interested in estimating a what? Mean? Mu. Okay. So you look at the problem and you say, okay, what am I really estimating here? Am I estimating a proportion or a percent? And if that's the case, and you're interested in a confidence interval, okay, so for this, remember, so if we're interested in a proportion, it's going to be a z interval, and it's going to be like that, right? So you say, oh, I'm trying to do a proportion. I want a confidence interval. Boom, this is the formula I need to use. All right? And it's a z interval, so the multiplier comes off the z table. But if you're trying to estimate a mean, then we're going to use our mean confidence interval formula, and that's going to be a t interval. Okay. So you just have to say, is it proportion or mean? Because that's going to drive your... And so proportion, sometimes also called percent, mean, sometimes called the average, right? Keywords to look for. And then, if your goal is to estimate the necessary sample size, okay, we had this here. The sample size here was, I think conservatively, it was 0.25, and I believe it was z alpha over 2 over e squared. That's what we used for proportion. And we just got this one a second ago. It was z alpha over 2 times the standard deviation over the error squared. So those are the two. All right. So you go into the problem and you say, okay, am I talking about proportions or means? Once you know that, you fall into this column and the other column. If it asks for a confidence interval, take the first row here. If you're trying to estimate a sample size, go down to the second row and use that estimator. Okay? All right. So we're pretty much out of time, but that should be enough. That should be enough to get you through all the chapters. You have everything you need to finish Chapter 9 homework at this point, basically. Okay? We're gonna barely jump into Chapter 10 tomorrow. And I think we're in pretty good shape, actually. Yeah. Okay. Yeah, it's true. It is a lot. But hopefully on a practical level, I think a lot of students find it easier because it's really a lot more formulaic and plug and chug kind of than maybe some of the probability problems and stuff that were really